Assalamualaikum warahmatullahi wabarakatuh. We are from Group 2. In this video, we would like to explain about the Group 13 and Group 14 elements in a periodic table. I will start the presentation and my name is Nur Aisha binti Mahlil and my matric number is 20763. So, let's start with the Group 13 element first. What is a Group 13 actually? Group 13 is sometimes referred to as a boron group and it is located in a column 13 of the periodic table. This group includes boron, aluminium, gallium, indium, thallium and also yttrium. In general, group that located the element is based on the valence electron of that particular element. So in this case, as it is in a group 13, therefore the valence electron is 3. For information, only boron having a metal-like properties and the rest will having a properties of a poor metal. Here are the some example picture of a group 13. We have indium, aluminium, gallium, boron and also the thallium. Next, we continue with the physical properties of a group 13. As it goes down the group, the atomic radius will be increasing. This is because as it goes down the group, the energy level will be increasing. Due to that, the shielding effect also will be increased, where the shielding effect is an effect that being caused by the core electron. Thus, the nuclear charge can be enough to attract the valence shell and resulting in the increasing atomic radius. Second, electronegativity first decreased from boron to aluminium, then it increased slightly from aluminium to thallium. This can be attributed to the poor shielding of the intervening d and f orbital. Next, ionization energy will be decreased as it going down the group. Ionization energy is the energy that required to remove an electron from the gaseous atom. Like I mentioned before, as it goes down the group, the electrons are more far from the nucleus and therefore they are more easier to be removed. Next, tendency to form oxidation number of positive point. The general oxidation state exhibited by the group 13 elements in a group are positive 3 and positive 1. As it goes down the group, the tendency to form a positive 1 ion will be increased due to the inert pair effect. Not just that, melting point will also decrease as it goes down the group. Boron has a high melting point because of the icosahedral structure. In the boron family, gallium has the lowest melting point. And the last one is the acidic nature of hydroxide will be reduced as it goes down the group of a boron family. Now, let's see the chemical properties of it. Chemical properties have it contains a reactivity, complex forming tendency, and also the covalent character. For the reactivity, we will see the reactivity of the group 13 elements with the oxygen, acid and alkalis, halogen, water, and also the metals. For the complex forming tendency, group 13 elements having a more tendency to form complex than S-block element due to their smaller size and also the more polarizing power. For example, boron can form many complex as it has an sp3 hybridized orbital and also the tetrahedral geometry. For example here, lithium aluminium hydride. And lastly, the chemical properties is a covalent character. There are 3 reasons. So the first one is the rule of the Fajans, where the smaller the cation is more for the covalence. Second one, they have a very high ionization enthalpies, which make the formation of ionic compounds high. And lastly, they have a relatively higher electronegativities, and hence the formation of a compound would not result in a higher electronegativity difference. So now let's see the reactivity of a group 13 towards the oxygen. All the elements of a group 13 will react at a high temperature and forming a thiouxide. So here is the equation. However, for the thallium, besides just forming a thallium trioside, it also will form a thallium dioxide. Boron is unreactive towards the oxygen in its crystalline form. However, a finely divided amorphous boron will react with the oxygen on heating to form a boron dioxide. Second, reactivity of a group 13 towards the halogens. All the elements in a group 13 can react with the halogen at a very high temperature to form a 3 halides. So here is the equation, and the X is represent the halogens group, the group 17. However, for the thallium, it only form thallium 3 fluoride and also the thallium 3 chloride. Next, reactivity of a group 13 towards the water. At the very high temperature, it will react with the steam. For the gallium and indium, it is not react with the water unless oxygen gas is present. And for the thallium, it will form a thallium hydroxide in moist air. Other than that, the group 13 also will be react with the metals. However, only 4 boron will be combined with metal to form a boride, and the rest of the elements of a group 13 are reluctant to combine with metal. Lastly, reactivity of group 13 toward acid and alkalis. Basically, group 13 elements will react with a strong oxidizing acid like a mixture of hot concentrated H2SO4 and HNO3 to give a boric acid. So here is the equation. And then for the boron, it resists the action of alkalis, where like natrium hydroxide and potassium hydroxide up to 773 Kelvin above, which they will form a borate. So that's all. Continue with the other part.
Hi, my name is Saravanan Kumravelu and my metric number is 206431. For the following part of this presentation, I will be introducing the binary compounds of group 13 elements. The first compound that I would like to introduce in my part is hydrides of group 13 elements. Hydride refers to the anion H-, but hydrides can be also used to indicate the compounds and ions which covalently attach to a less electronegative element. The first group 13 hydride that I would like to discuss is hydrides of boron. There are actually a lot of boron hydrides, but the simplest hydride of boron is known as diborane. This compound consists of 2 boron atoms attached to 6 hydrogen atoms, and commonly this diborane exists in the form of gas. Meanwhile, higher boranes such as borane with at least 5 boron atoms exist in the form of liquid. Meanwhile, boranes with at least 10 boron atoms exist in the form of solid. And the common properties of this borane is they are colorless, flammable, and diamagnetic. To obtain the diborane, there is a simple reaction that we can undergo to produce diborane. 3 lithium borohydride reacted with 4 boron trifluoride to produce 3 lithium tetrafluoride borate and also 2 diborane. Similar to other chemical compounds, diborane also has its own reactivity, and its reaction with oxygen produces boric acid, and the reaction with water will also produce boric acid, but apart from the boric acid, hydrogen gas will be also produced when diboranes reacted with water. The next chemical property of diborane is that this compound is Lewis acid. Lewis acid refers to a substance that accepts pair of electrons, specifically non-bonding electrons, and the reason why boron hydride or diborane is Lewis acid is because this compound is electron deficient compound and it gains its stability through back bonding. So it accepts a lone pair very easily. Commonly, boranes can be used in various fields, and here are three examples of diboranes or even other boranes application. The first one is rocket propellant, or also known as fuel, and second one is as a reducing agent, and third one is rubber vulcanizer. In addition to boron hydride, I would like to also introduce or talk about aluminium hydride and gallium hydride. Aluminium hydride, or also known as alane, and gallium hydride, also known as galane. These three are also hydrides of group 13 elements. And we will discuss about these two compounds with a series of certain topics. And the first topic that I would like to touch is synthesis. To produce the aluminium hydride or alane, the reaction is lithium aluminium hydride reacted with aluminium trichloride to produce aluminium hydride. Meanwhile, for galane, usually it is quite challenging to synthesize galene through a simple reaction. But the common types of gallium hydride that can be synthesized easily is a digalene, which means there will be two gallium atoms attached to the hydrogen atoms. And the next part is reaction in water. Uh, Aluminium hydride reacts in water very violently. Same goes to the gallium hydride. They also react in water very violently. The reason is because when hydride ion reacts in water, it produces aluminium hydroxide ion and also hydrogen gas. This hydrogen gas, when it is liberated, it will look as if the reaction caused a simple explosion. Therefore, the reaction of aluminium hydride and also gallium hydride with water is identified as a violent reaction. The next part is characteristics of aluminium hydride and gallium hydride. Aluminium hydride and gallium hydride both are said to be more hydrate compared to borane. The reason is because boron is a more electronegative atom. Therefore, the hydride of the hydride ion that is being attached to the boron will have less electron density. When the electron density is less, the ability to act as a reducing agent or even a nucleophile in a reduction process, that ability will decrease, and that's the reason why aluminium hydride and gallium hydride more hydrate compared to borane. This is the main reason is because aluminium hydride and gallium hydride are less electronegative compared to borons, and therefore the ability for aluminium hydride and gallium hydride to act as a reducing agent is higher compared to borane, which is simply known as the hydric property of these compounds. And for aluminium hydride, it is soluble in ether, and usually in various reactions, the aluminium hydride will be used together with ether. The reason is because if they reacted with water, the reaction will be very violent, and therefore the reactions will be conducted in the ether. And why ether is because aluminium hydride soluble in ether. Gallium hydride also which reacts violently, and another characteristic for gallium hydride is that it undergoes hydrolysis process in water. Hydrolysis refers to the breakdown of a compound through the reaction with water. And the next part, we will see the structure of aluminium hydride and also gallium hydride. These two compounds are actually similar in terms of structure, and commonly these two structures exist in the form of tetrahedral. And the bonding of these two compounds are covalent bonds, and The application of these two compounds are usually they are used as a reducing agent in reactions as in the reaction where the carbonyl compounds and also carboxylic compounds need to be reduced into alcohol. And the reason why they act as reducing agent is because these two compounds have the tendency to donate the hydride ion to the reacting to the reacting compounds. The following binary compound that I would like to discuss is nitrate of group 13 elements. One of the nitrate that are present in the group 13 binary compounds is aluminium nitrate. Aluminium nitrate commonly exists as crystalline nanohydrate. They appear in the form of colorless and also odorless. Usually, aluminium nitrate are water soluble as well. And to prepare the aluminium nitrate, the reaction is adding nitric acid to aluminium trichloride. And the reaction in water of aluminium nitrate and water, it produces aluminium oxide and 6 nitrogen dioxide and also oxygen. And the reaction with sodium hydroxide produces aluminium hydroxide and also sodium nitrate. Aluminium nitrate can be used as oxidizing agent and also corrosion inhibitors. Another group 13 binary compounds that is associated with the atom N, which is atom N, is boron nitride. Similar to graphite and diamonds, boron nitrides are also a very strong element. This is because they are thermally and also chemically resistant. And the common properties of this boron nitride is that they are soluble in basic molten salts, insoluble in acid, good electrical insulator, and good heat conductor. As we can see here, the 3D structure of boron nitride, it contains covalent bonds and also van der Waals bonds. And this is the structure that allows boron nitride to be thermally and chemically resistant. And this compound commonly used as abrasive for high temperature application. The third binary compounds that I would like to discuss is sulfide of group 13 elements. Aluminium sulfide, it's a gray solid with a smell of sulfur or even a smell of rotten eggs. And this compound is actually very sensitive to moisture. And to prepare this aluminium sulfide, the reaction is 2 aluminium reacted with 3 sulfur to produce aluminium sulfide. And the reaction of aluminium sulfide with water will give 2 aluminium hydroxide and also 3 hydrogen sulfide gas. And aluminium sulfide can be also reacted with hydrochloric acid, and the reaction will produce 2 aluminium trichloride and also 3 hydrogen sulfide gas. And aluminium sulfide can be used as semiconductors, photoconductors, or light emitters. And this compound is actually an ionic compound, and as we can see here, this is an example of aluminium sulfide, which exists in the form of gray solid. In addition to aluminium sulfide, there are also other sulfides in the group 13 binary compounds, such as sulfides of gallium, indium, and thallium. But these sulfides are numerous and varied. However, the properties of these compounds are very similar to the aluminium sulfide.
Hi, my name is Wana Atika, and I'll be continuing presenting about the binary compounds of group 13 elements. Okay, first off, let's start with oxides of group 13 elements. Okay, we'll start with boron oxides. Okay, the general formula for boron oxides is B2O3, which is formed when boron is heated with excess oxygen. So as you can see from the chemical equation, boron will react with oxygen to form boron oxide. And boron oxide can be made from dehydration of boric acid. Okay, you can refer to the chemical equation to see that the dehydration of boric acid will form boron oxide and water. And since this is a reversible reaction, so when boron oxide reacts with water, it will reform to boric acid. The structure for boron oxides is white glassy solid. So boron oxide is a solid which is normally found in its amorphous form. Okay, this is because the structure for elemental boron itself do not pack tightly together, so it has many voids between it, which is why the structure for boron oxide is usually found in amorphous form. As you can see in the structure below, there are many voids in the structure which makes it amorphous. However, it can still be crystallized under prolonged heat, and the crystalline boron oxide consists of an ordered network of boron oxide units joined together through oxygen atoms. Okay, next, we will look into the other elements of group 13 oxides. Okay, so the general formula is M2O3, in which M can either be aluminum oxide, gallium oxide, indium oxide, or thallium oxide. Okay, so these are the chemical formula for each compound, and they are also called trivalent oxides. The chemical properties of the oxide follow the trend from acidic to basic when moving down the group. Now, as you can see in the table, from boron oxide to thallium oxide, there is a gradual change from acidic to basic. Boron oxide is the only acidic compound in group 13. For aluminum oxide and gallium trioxide, they are amphoteric, which means that they are able to react as both acid and base. Indium trioxide and thallium trioxide are both basic compounds. Okay, for aluminum oxide, the most stable form is alpha alumina, or also known as corundum. Corundum is the crystalline form of aluminum oxide, and it is in its highest oxidation state, so no more oxidative reactions are possible to happen. Alpha alumina is a very hard, refractory, and amphoteric material. Okay, so like I've mentioned just now, aluminum oxide is amphoteric, which means that they can react as both acid and base. So therefore, alpha alumina is also an amphoteric material. Next, for gallium trioxide, its most stable form is alpha gallium trioxide. It has the same structure as its analogous corundum, which is the alpha alumina. Okay, lastly, we will look into the application for group 13 oxides compound. Okay, first off, we have boron oxide. Boron oxide is the main constituent of borosilicate glass. The glass has low thermal expansivity due to its strong BO bond, okay, which means that when it is heated, the glass expands as a reaction to the heat very slowly. Thus, it has low thermal expansivity. So because of this characteristic, it is widely used in the making of heat-resistant laboratory glassware. For aluminum oxide, it is a valuable element in the formation of rubies and sapphires because its crystalline form, alpha alumina, or economically known as corundum, is the base element for this gem. Okay, that is all for oxides of group 13 elements. Next, we will look into the highlights of group 13 elements. Firstly, we will look into the boron trihalides. Okay, its general formula is BX3, where X is the halogen. So it can either be boron trifluoride, boron trichloride, boron tribromide, or boron triiodide. Okay, boron trihalides is formed by heating boron with excess halogen. Like you can refer to this chemical equation. You can see that boron react with any halogen. It can be fluoride, chloride, bromide, or iodide. It will form into boron trihalides with three halides atom. Okay, and the physical properties of boron trihalides is that they are very volatile, which means that they are easily evaporated at normal temperature. Okay, as you can see in the table, boron trifluoride and boron trichloride are gases because they have low boiling point, which are negative 100 degrees Celsius and 13 degrees Celsius respectively. While for boron tribromide, it is a volatile liquid with 91 degrees Celsius boiling point, and boron triiodide is a solid with low melting point at 50 degrees Celsius. The chemical properties for boron trihalides is they have an incomplete octet and they are Lewis acids. This is because boron trihalides has only 6 electrons in their valence shell. Hence, they can accept a pair of electrons in the vacant p orbital to complete its octet. Lewis acidity for boron trihalides is increasing from boron trifluoride to boron tribromide. Okay, so in other words, boron tribromide is the strongest Lewis acid. If you notice, this order is in contrast with the electronegativity trend in halogen group, where fluoride is has the highest electronegativity and bromide has the lowest electronegativity. This is because in boron trifluoride, boron undergoes back bonding with fluorine atom. Okay, back bonding is a type of bond that occurs between atoms in a compound in which one atom has lone pair of electrons, which is the fluorine atom, and the other has a vacant orbital, which is boron, since it has a vacant p orbital placed adjacent to each other. So as a result, boron gain electrons from fluorine atom because both boron and fluorine are similar in size. So boron trifluoride can undergo back bonding with fluorine atom. But on the other hand, boron and bromine have different atomic size, so they cannot undergo back bonding. The smaller the halide atom, the more effective the back bonding can occur, and it shows a less tendency to accept a pair of electrons. Okay, which is why the ability of back bonding decreases when moving down the group, because when moving down the group, the size of halides increase, hence making the molecules more acidic, which means that its tendency to accept a pair of electron increasing. So we can say that the tendency of back bonding decrease as the size of halogen atom increase is due to the large energy difference. To make it more clearer, we can take a look at this diagram. Okay, we first look at the boron trifluoride. Okay, as you can see that boron atom and fluorine atom are similar in size, so they can overlap with each other and form an effective back bonding. However, for boron tribromide and boron trichloride, they have a significant difference in size, so they are not able to overlap with each other, which then creates a very weak or not effective back bonding. So when they cannot form back bonding, their tendency to accept a pair of electrons will increase. Thus, this is what Lewis acids mean. So when their tendency to accept a pair of electrons start to increase, means that they are a strong Lewis acids. Okay, next, for the structure of boron trihalides, it is a trigonal planar and it exists in monomeric form, which means that they are not able to undergo dimerization. This is because boron is small in size and it cannot accommodate more halogen atoms. Therefore, it cannot form a dimer. The structure below is the monomer form of boron trifluoride. Okay. Next, we will look into the other elements of group 13 halides. The general form is MX3. So it can either be aluminium, gallium, indium, or thallium trihalides. And the formation for these trihalides is as shown here. Okay, M represent the elements from group 13, so either aluminium, gallium, indium, or thallium, and X represent the halogen. So when they react with each other, they will form MX3. And the properties for fluorides compound in group 13 is that they are ionic compound, and so they have a high melting point because it requires a lot of energy to break the bond in an ionic compound, and it has low solubility in non-polar solvent, and they do not act as Lewis acids. But for chlorides, bromides, and iodides compound in group 13, they are covalent compound, so they have low melting point, which is in contrast with fluorides, because in covalent compound, the electrostatic force between the atom is weak, so it requires low energy to break the bond. And they have high solubility in polar solvent, and they are also an excellent Lewis acid. The structure for the other elements of group 13 halides is the same like boron trihalide just now, which is trigonal planar, but it exists in dimeric form. Okay. Why did I say this? Let's take aluminium trichloride as an example. Okay, aluminium trichloride is an electron deficient compound because it has only 6 electrons in the valence shell. So it has strong tendency to gain another 2 electrons to complete its octet. And the electron deficiency of aluminium atom in the aluminium trichloride is completed by the formation of coordinate bond between the lone pair of chlorine atom from another aluminium trichloride molecule and the vacant p orbital of aluminium atom. Thus, it forms dimer. Okay, like as you can see in the structure here, if you notice the difference in the structure of dimer aluminium chloride and boron trihalide just now, boron trihalide is a monomer, so it only has one molecule. But for dimer aluminium chloride, it will make a reaction of between two of the same molecule to make into one molecule. So, which is why this has two of the same molecule forming a one molecule. So that is what called as dimer. And this happened because aluminium being a bigger atom, so it can compensate its electron deficiency by undergoing dimerization, and this goes the same for gallium, indium, and thallium. Lastly, for the application of highlights of group 13 elements, first have boron tribromide. Okay, boron tribromide is used in electronic industry in pre-deposition processes for doping in the manufacture of semiconductor. Okay, so boron tribromide are widely used in the doping in manufacturing semiconductor. Okay, this is an example of semiconductor. As for aluminium trifluoride, it is used as a flux in welding applications as well as in ceramic grease. Okay, that is all for binary compounds of group 13 elements. We will next move on to group 14 elements.
Okay, next I will explain about the introduction of element group 14 and also the properties of element in group 14. Okay. Okay. So basically, what is a element in group 14? So element group 14, or known as a carbon family. Why it called it as a carbon family? Because if we can see in this periodic table, so basically the first element that been assigned, or we can say in arranged in a group 14, is carbon. Okay, and yeah, there's a lot of elements. Okay, so basically the group 14, the all element that are included in group 14, which are carbon, silicon, germanium, tin, and plumbum. And the reason why all of these elements are called as a carbon family, because of they have a same 4 valence electron, and also the scientists assume that it's called a carbon family because all of these different elements are giving us same properties, as same as a carbon element, and that's why it called a carbon family. Okay, all right, so let us jump back to this slide. Okay, so basically these are like a roughly a picture of the elements. This is carbon, okay, and then this is a silicon and germanium, and this one is a tin, and the last but not least is plumbum. All right, so why element group 14 is very important. First of all, we need to know that element group 14, the element in this group are being used in the semiconductor technology, as we can see that yes, it is true, because we know that all of the semiconductor technology, the main the main element that they use, like the commonly we know, is like carbon, silicon, germanium. So yeah, these elements are very important for them, okay, to for them to create a semiconductor. All right, so the element group 14 are located very nearly in the middle of the periodic table, which is in its left are metal and its right are non-metal. So this one is a for group 14. Okay, so you can see it on the left side, they contain of the non-metal elements, and but for the right side is a metal element. All right, now we will jump to the properties of element group. Okay, all right, the carbon family, which is the element in this group 14, is consists of one non-metal, which is carbon, and two metalloids. So basically two metalloids is like half of it is metal, and it's like a combine between a metal and non-metal, like that. Okay, silicon and germanium, and two metals, which is tin and lead. Okay, so in other words, the elements gain metallicity moving down the group, which is if we go down to the group, it become more metal. So it's because we know the trend is from carbon to the plumbum, is from non-metal to the metal. Okay, so the element of group 14 in overall are stable and tend to be fairly unreactive. Okay, so the element group 14 tends to form a covalent compound. All right, because we know that this group has a 4 valence of electron, so they can share their electron, because we know the covalent compound, basically covalent is a bond that share their electron. Okay, all right, The element in group 14 carbon family element have much higher melting point and boiling points than the group 13 element. Alright, next we will go to the element group 14 facts. So in this table we will compare. Okay, alright, for the first one is the melting point. Okay, for the melting point for carbon is 3500 degrees Celsius, and when we go down to the table, we can see the trend that the melting point become decreases. Why it is because of the attraction of the carbon itself, the nucleus, the attraction between the nucleus and the electron are very stronger because for carbon. And for plumbum, I'm sorry, for plumbum, the attractions of the nucleus and the electron are very weak. This is because of their size. Okay, we can say that the carbon atoms are more smaller than the plumbum, and the trend for the group 14 in the periodic table, when we go down, so the size of atom will become decreases. Will become increases. Okay, because we need to know when the atom is small means that they have a very good attraction, the strong attraction, which is it needed a lot of energy to break down the attraction, means the melting point will become increased. Same goes for the boiling point. Okay, all right, for the density, okay, we can see that carbon are more less than the plumbum itself. Okay, and for the ionization energy, we can see carbon is the most increases, and when we follow the trend until plumbum, I'm sorry, it will decrease. Okay, so yeah, like I said, because of the attraction itself that make a higher energy of the ionization itself. Okay, all right, now next is the atomic radius. So yeah, the atomic radius for carbon is, you can see, is very small compared to plumbum. Okay, when we follow the trend, we go down for the group 14, we can see the atomic radius for the atom itself are decreasing. It are increasing. Okay, all right, so yeah, this one is ionic radius, and this is basically the usual oxidation number, means that what are the oxidation number that they can achieve, which is we have for carbon we have the +3, -4, and for silicon we have only +4, and for germanium is +2 and +4. I mean, each element in this group 14 will give a different oxidation number. Okay, and for the hardness, we can say that carbon is the more hardness, which is this carbon, it's more like what you can say, are very hard than the others element in the group 14. Okay, so yeah, most is like it's a unit that calculate the hardness of a structure itself. Okay, so for the crystal structure, yes, for the crystal structure, it's for carbon it is a cubic. Okay, and for silicon and germanium is cubic also, but the for carbon is a diamond. Okay, and then for stannum, which is tin, is a tetragonal, and for plumbum is a face center cubic.
Binary compounds of group 14 elements. Hydrides of group 14 elements. All the elements of group 14 elements can form hydrides. They are chemical compounds composed of hydrogen atoms and group 14 atoms. On going down the group, the case of hydride formation decrease. As you can see from the table, the formation of hydrides for carbon are alkanes, alkynes, and also aromatic hydrocarbons. Silicon, silane, germanium, germane, tin, stannum, distannum, lead, plumbum. So in this section, we will be focusing on tetrahydrides and a little bit of hexahydrides. So the general formula for tetrahydrides is XH4. X represent group 14 elements and H4 is hydrogen. So the thermal stability for tetrahydrides, they are decreased down the group because of the increasing in size of metal. As the size of metal increase, the bond length between the atoms will be increased and the bond strength become decreased. So the thermal stability become decreased. Tetrahydrides also, their ability to act as reducing agent increase from CH4 to PbH4. So the abnormality in trend of SiH4 is they cannot be explained on the basis of electronegativities, can be explained on the basis of polarity as high H bond and availability of d orbitals of silicon. Silanes are more reactive than alkanes and strong reducing agent. They are easily hydrolyzed by alkaline solution to liberate H2 and also Na2SiO3. They also can hydrolyze by natural water to form H2SiO3 and 4H2. So the chemical properties for silane is they are highly toxic gas with a repulsive odor and it is spontaneously flammable in air. Next, hexahydrides. The general formula is X2H6. For example, ethane, C2H6. They are commonly found alongside methane in natural gas, and other hydrides are even less stable than tetrahydride. Some application for hydrides of group 14 elements are methane. They are used for heating and cooking purpose and for power utilities, gas turbines. And silane, they are used in some fiberglass and composites to improve mechanical strength and electrical properties. Next, oxides of group 14 elements. All the elements of group 14 can form oxides when heated in oxygen. They are mainly of two types of oxide, which are monoxide and dioxide. For example, silicon monoxide is formed by reduction of silicon dioxide, react with silicon to produce silicon monoxide. Lead also can form another oxide called tri-lead oxide or red lead. It is obtained by heating lead monoxide with excess of air or oxygen at 673 Kelvin. Properties: acid-base character. The oxides in higher oxidation state of the elements are generally more acidic than those in the lower oxidation state. So as we move down the group, the acidic character decrease. So among dioxide, carbon dioxide and silicon dioxide are acidic. Germanium dioxide and tin dioxide is amphoteric, and lead dioxide is a base. So as carbon dioxide and silicon dioxide are acidic character, they can only react with base. So for example, carbon dioxide can react with sodium hydroxide to produce Na2CO3 and water. Same goes with silicon dioxide. So as germanium dioxide and tin dioxide are amphoteric, they can both react with base and also acid. While for lead dioxide, they can only react with acid as they are base character. Next, properties: reducing and oxidizing agent. So carbon monoxide is the strongest reducing agent among the monoxide, as the positive force state of carbon is the most stable, and it also can be used in the extraction of many metals from their oxides. For example, the zinc monoxide react with carbon monoxide to produce zinc and carbon dioxide. While for oxidizing agent among the dioxide, lead dioxide is the strongest, as the positive to oxidation state of lead is the most stable due to the inert pair effect. For example, lead dioxide react with hydrochloride to produce PbCl2, Cl2 and water. Some application for oxide of group 14 elements are carbon dioxide. They can promote the growth of plant and also refrigerant. And next example, carbon monoxide. They can be used in metal fabrication, used in fuel gas mixtures with hydrogen and other gases for industrial and domestic heating. In chemicals, they can be used in the manufacture of a variety of chemicals such as acid, ester, and alcohol. Halides of group 14 elements. The elements of group 14 can form halides such as tetrahalides and dihalides. So for tetrahalides, the general formula is MX4. M stands for the group 14 element and X is stand for the halogen atom. So most of the tetrahalides are covalent compound. The central atom in the halides undergo sp3 hybridization and the molecule is tetrahedral in shape, except for tin tetrafluoride and lead tetrafluoride. They are ionic compound. So for the thermal stability, they decrease with increasing in atomic number. When the group 14 element is different but the halogen atom is the same, for example, we use chloride. And also it will also decrease with increasing size of halogen atom when the halogen atom is different but the group 14 element is the same. So fluorocarbon CS4 is very stable due to the strength of its carbon fluoride bonds. So as you can see from this picture, the carbon halogen bond, the length is increasing from fluorine to iodine. So as the bond length increase, the bond strength decrease. So as carbon fluoride, the bond length is smaller than the others, so the bond strength is higher. So it is very stable. So for hydrolysis reaction, tetrahalides are readily hydrolyzed by water. For example, silicon tetrachloride will react with water to produce SiOH4 and hydrochloride. But for CCl4, they are not hydrolyzed by water as they don't have the carbon does not have the d orbital and hence they cannot extend its coordination number beyond number 4. Next, forming of complex. All elements can form complex except for carbon. The reason for the carbon is the same as the hydrolysis reaction they don't have for CCl4. So for other elements, they can form complex because the availability of the vacant d orbital, so they can increase the coordination number to 6. So for example, silicon tetrafluoride react with hydrogen fluoride to produce H2SiF6. Next, tetrahalides of germanium, tin, and lead, they can behave as Lewis acid, but tetrahalides of carbon cannot. So for example, tin tetrachloride react with chloride ion to produce hexachlorostenane ion. For the halides, the general formula is MX2. All can form dihalides except for carbon and silicon. So the thermal stability increase steadily due to the innate pair effect. Some applications for halide for group 14 elements are carbon tetrachloride CCl4. They can be used in dry cleaning and manufacturing refrigerants, and also silicon tetrabromide. They can be used in ceramics manufacturers.
Okay, now we will go to the sulfates of group 14 elements. The first example is lead sulfate. The general formula is PbSO4 and it has an ionic bond where Pb2 plus is an anion and SO4 2 minus is a cation. Lead sulfate is a white solid, appears white in a microcrystalline form. It is also known as fast white, milk white, sulfuric acid lead salt, or anglesite. It can be prepared by treating lead oxide, hydroxide, or carbonate with warm sulfuric acid, or treating a soluble lead salt with sulfuric acid. Alternatively, it can be made by the interaction of solution of lead nitrate and sodium sulfate. Lead sulfate has a crystal structure of orthorhombic and its melting point is at 1170 degrees Celsius. Lead sulfate will decompose when heated above 1000 degrees Celsius and it will produce lead oxide and sulfur trioxide. Lead sulfate is toxic by inhalation, ingestion, and skin contact. Cumulative poison and repeated exposure may lead to anemia, kidney damage, and others. Solubility of lead sulfate in water. Lead sulfate is poorly soluble in water. The water dipole strength is too weak to separate the anions and cations of the lead sulfate because lead ion and sulfate ions are big. And the bigger anion will stabilize bigger cation strongly, which makes lattice energy high. Solubility of lead sulfate in other substances. Lead sulfate will dissolve in concentrated nitric acid, hydrochloric acid, and sulfuric acid, producing acidic salts or complex compound. It will also dissolve in concentrated alkali, giving soluble tetrahydroxidoplumbate 2 complex. The next example is tin sulfate. Tin sulfate has a general formula of SnSO4. The type of bond is ionic bond, where Sn2 plus is an anion and SO4 2 minus is a cation. Tin sulfate is a white solid that can absorb enough moisture from the air to become fully dissolved, forming an aqueous solution. This property is known as deliquescence. Tin sulfate can be prepared by a displacement reaction between metallic tin and copper to sulfate. The reaction will take place in a diluted solution sulfuric acid. Structure of tin sulfate. In the solid state, the sulfate ions are linked together by OS and O bridge. The tin atom has 3 oxygen atoms arranged pyramidally at 226 pm with the 3 OS and O bond angles of 79 degree, 77.1 degree, and 77.1 degree. Its crystal structure is primitive orthorhombic. Tin sulfate have a melting point at 378 degrees Celsius, which is equivalent to 712 Fahrenheit and 651 Kelvin. It will decompose in air at 230 degrees Celsius, producing tin dioxide and sulfur dioxide. Tin sulfate will soluble in water and diluted sulfuric acid. This is the application of the sulfates of group 14 elements. The first one is lead sulfate. Lead sulfate is used in lithography and in weighting fabrics and is also used as a paint dryer. The second one is tin sulfate. It is used in acid tin plating, both lacquer finishing and drawing of steel wire. It delivers a high current efficiency and smooth fine grain deposit. Next is nitrites of group 14 elements. The example are silicon nitride. The general formula of silicon nitride is Si3N4 and it has a covalent bond. Silicon nitride is a white, high melting point solid that is relatively chemically inert, being attacked by dilute hydrogen fluoride and hot sulfuric acid. It is very hard and has a high thermal stability, and most importantly it is insoluble in water. We can prepare silicon nitride by heating powdered silicon between 1300 degrees Celsius and 1400 degrees Celsius in a nitrogen environment. Other than that, it can be prepared by a carbothermal reduction of silicon dioxide in nitrogen atmosphere at 1400 degree until 1450 degrees Celsius. This is a structure of silicon nitride. There are three crystallographic structures of silicon nitride designated as the alpha, beta, and gamma phases. The alpha and beta phases are the most common forms of silicon nitride and can be produced under normal pressure conditions, while the gamma phases can be synthesized under high pressure and temperature, and it has a hardness of 35 gigapascal. If you can see, the first picture is alpha phases, the second picture is beta phases, and the last picture is gamma phases. Alpha phases have trigonal structure, while beta phases have hexagonal structure, and gamma phases have cubic structure. Application of silicon nitride. In electronics, silicon nitride often used as an insulator and chemical barrier in manufacturing integrated circuits to electrically isolate different structure, or as an edge mask in bulk micromachining. In automobile industry, it is used as a material for engine parts. Those include diesel engines, glow plugs for faster startup, pre-combustion chambers for lower emission, faster startup, and lower noise. Okay, I think that's all from us. Thank you for listening.